Okay, so today I'm going to start by explaining how to use numpy.polynomial and scipy.signal.transfer function, how to multiply transfer functions in series. So we're going to start by looking at how to multiply polynomials inside Python. So I've already imported our numpy.polynomial as poly. And then one thing to note about using numpy.polynomial, we have to have our polynomials in increasing exponent order. So let's say we want a polynomial of 1 plus 2s plus 3s squared. And then we want to multiply this by a polynomial of, let's say, 3 plus 2s plus 1s squared. So we can see that this multiplies our polynomials and our exponents are in increasing order. So if we start thinking about how to multiply transfer functions inside of Python, we need to have our exponents in decreasing order. So we're going to create a function to transfer between polynomials and transfer functions to make it easier for ourselves. So we're going to define TF, our transfer function, to a polynomial with respect to our transfer function. Oh my goodness. And then we want to return our numerator and our denominator. So we're going to have poly of our transfer function numerator, and we're going to do the same thing for our denominator. And now we can create a transfer function to try this out. So let's say that we want a transfer function and our numerator to be 1s plus 2. So like I said, in transfer functions, we have to have our exponents in decreasing order. So then let's say in our denominator, we want a transfer function of 1s squared plus 2s plus 3. So this gives us our numerator as an array, and then it also gives us our denominator as an array. So let's set this equal to our first transfer function. And then we can try out our TF to poly of our transfer function 1. So we can see that our numerator and denominator are still in our transfer function form. So we actually have to use Python indexing to change around our exponent order. So we want to say that we're going from our start to our end, and then we're going to use -1 to tell it to flip the exponents. And we are going to do the same thing for our denominator. So now if we try this, we can see that our numerator and our denominator get turned into polynomial form. So now let's create a function to do the opposite. So we're going to change our polynomial to a transfer function, and we need to give it our numerator and our denominator. And then we need to return TF of our numerator coefficients. There we go. And we're going to do the same thing with indexing from our start to our end, and then -1. We're going to do the same thing for our denominator, and the same thing for our indexing. So now we can set this equal to our numerator and our denominator. Excuse me. And then we can try out our poly to transfer function of our numerator and our denominator. And we can see that this changes it back into our transfer function form. So now if we want to multiply transfer functions together, we're also going to create a function to do that. But first, let's give our code a second transfer function. So we're going to say that this transfer function is, in our numerator, let's say we have 2s squared plus 3s plus 1. And in our denominator, we have, let's say, 2s minus 3. Sure, why not? So now we are going to define our transfer function multiplying our transfer functions. MULTI. and we have to give this our transfer function 1 and our transfer function 2. And then we want to tell it that our numerator 1 and our denominator 1 are equal to our TF2 poly of our transfer function 1. And we're going to do the same thing for our numerator 2 and denominator 2. And we're going to use our transfer function 2. And then we need to return our poly to transfer function of our numerator 1 times our numerator 2 and our denominator 1 times our denominator 2. Alright, now let's try this out. So if we do TF multiply of our TF1 and TF2. So we can see that this now multiplies our transfer functions together, and this array will be our numerator values, and then the next array will be our denominator values. Okay, so now we are going to derive the transfer function for a PID controller, and then we're going to use Python to generate it. So for our PID controller, we know that we have some Kc value, and Kc is our proportionality constant, and this is multiplied by our error. And in this case, we're doing height, so it's going to be our height set point minus our actual height. That's what our error is. Then we have plus 1 over tau I times the integral from 0 to our final time of our error. And then we are integrating dependent on time. Plus we have tau d times the change in our error over the change in our time. So this is our proportional integral derivative control. So this is our PID controller. So we are going to set this equal to our little p. And we know that all of our errors have to be our derivation variables. So we're going to mark all of those. And now we can say that our error is in the Laplace domain. So meaning that we are going to call our error signal our little e. It's in the Laplace domain. So now we're going to take the Laplace transform of this function. So we're going to call this our big P. And we're going to have our big P equal to Kc times our little e plus 1 over tau I. And then the Laplace transform of an integral is the Laplace variable divided by s. So we're going to have e over s plus the Laplace transform of a derivative is just multiplied by s. So we're going to have tau d se. So that's going to be the Laplace transform of our function. So now we're going to simplify this a little bit, and I'm going to pull e out of the parentheses. So we're going to have big P is equal to Kc times 1 plus tau I times s, and that's 1 divided by tau I times s, plus tau d s, and then we pulled e out. So now we can go one step further in simplifying this and create a common denominator for our parentheses. So we can say that our big P is equal to Kc times tau I tau is plus 1 plus tau d tau I s squared over tau I s. We still have our e on the outside. So I'm going to go one step further and write this in decreasing order of our exponents. So we're going to have tau d tau I s squared plus tau I s plus 1, and it's all over tau I s, and we have e on the outside. Okay, so now we are going to use the equations that we just found on the whiteboard for our PID controller to define a function for our PID controller. So we're going to define PID. In this, we have to we have to start by giving it our independent variable kc, and then our dependent variables tau I and tau d. And now we are going to return the equations that we did. So we are going to return our transfer function of our numerator, which was tau d time, or let's do kc times tau d times tau I. So again, when we're working with transfer functions in Python, we have to make sure that our exponents are in decreasing order. So we had on our whiteboard, we had kc times tau d times tau I, and then it was s squared. And then our next part of this will be kc times our tau I. And then finally, we just had plus 1, so we're just going to do kc. And now to do our denominator, we need to have tau I, but we also need to have 0 to tell our code that we have tau I s instead of just having tau I by itself. So now we can try this out. So let's do PID, and we're just going to pick some random numbers. So let's say our kc is 1, let's say our tau I is 10, and let's just say our tau d is 1 also. So this gives us our transfer function of our PID controller as our numerator being 1s squared plus 1s plus 0.1, and then our denominator is just 1s. So now we're going to create a block flow diagram of our process under feedback control, and we're going to derive the transfer function for the controlled variable in respect to our process, our control, and our measurement device. So we're going to start out by looking at our first tank. So our first tank is going to be a transfer function of R1 over A1 times R1s plus 1. So that's our first tank. And we know that we have some flow going in, and we're going to call this Q1. And once the flow goes through this tank and through our transfer function, it's going to output our first height, so we're going to call that H1. And then it needs to go through another transfer function of just 1 over R1 to output our second flow, so we're going to call this our Q2. And now Q2 is going to go through our second tank, which is very similar to our first tank, and it's going to be R2 over A2 R2s plus 1. And just like it went through our first tank and outputted our first height, the flow is going to go through our second tank and through the transfer function to output our H2 value. And this will be our H2 value in the Laplace domain. So now, if we want to track what our H2 value is, we can send this through a measurement device. So typically, measurement devices are very complicated and you have to convert a lot of units. But for simplicity, we're just going to say that our measurement device does all of the work for us and it outputs our units in meters. So we're going to have our measurement device here. And we are just going to say that our measurement device multiplies by 1 since we're already given our unit in meters. Then if we know our H2 is going to go back to the front of our block flow diagram. And we also have a H2 set point that is being told. So we are going to have a controller right here that tells us if our H2 is higher or lower or plus or minus of what our H2 set point is. And this controller is going to output our error signal in the Laplace domain. And then it is going to go through our PID controller and back through our entire system. So to find the forward transfer function for this system, we're going to multiply by all of our smaller transfer functions. So we're going to be multiplying our PID, our first tank that outputs our height 1, and then our height 1 that outputs our Q2, and our Q2 that outputs our H2. So now if we look at it, we're going to be multiplying all of these so we can see that we can just eliminate our R1s. Since one's in the denominator and one's in the numerator, we can just simplify that. And we also can see here that this part of this transfer function is equal to our PID controller. That is what we found in the last part of our video. Okay, so now we are going to find our transfer function for the forward direction of our system. So if we want to do this, we need to find the transfer function between between Q1 and Q2 to start out. So we know that our Q1, Q2 transfer function is going to be, our numerator is just 1, since our R1 canceled out from the numerator and the denominator. And then our denominator is going to be A1 times R1, and then we have plus 1. So we need to initiate values for our A1. We're just going to keep it simple, and we're going to say that A1 is 1. And then let's also initiate our value for R1. And we're just going to keep this one simple too, and we're just going to say that it's 2. And then we also need to find our transfer function between Q2 and H2. So we know this is going to be our transfer function of our numerator, which is R2. And then our denominator will be A2 times R2, and then plus 1. We are also going to initiate values for A2, and we're just going to keep this simple, and we're going to say that A2 is also 1. And then we can initiate our value for R2, and we're just going to say that R2 is also 2. So now we can use our TF multiply that we initiated earlier to multiply the two of these together, since we know that our forward direction transfer function is going to be the transfer function of our PID controller times the transfer function between Q1 and Q2, and then the transfer function between Q2 and H2. So let's start out by doing our TF multiply of our Q1, Q2 times our Q2, H2. And this will give us the transfer function of 0.5 on top, and then our denominator is going to be s squared plus 1s plus 0.25. So then if we also multiply this by our PID controller, we can do TF multiply again, and then we're going to say our PID, and our PID is KC, tau I, and tau D. And we are going to multiply it by what we already just figured out. So let's initiate our values for KC, tau I, and tau D. So we're going to say that KC is equal to 1. And then we can say that our tau I is equal to, let's say, 10. And then we are going to say that our tau D is equal to 0.1. So now this gives us the transfer function of our numerator being 0.5s squared plus 0.5s plus 0.05, and our denominator is going to be 1s cubed plus 1s squared plus 0.5s plus 0. So this is going to be the transfer function for our system in the forward direction. So we are going to name this transfer function forward. Okay, so I have our original process drawn real small up here on the top of our board, and we already found the transfer function of our forward process. Now we need to find the transfer function for our entire process. So typically we use the variable g to describe transfer functions, so we're going to redraw this process to show our g values. So first we have our h2 set point coming in, and then we go through our plus minus controller, which outputs our error signal. And then we go through our PID controller, which is typically called our GC. And then we go through our process, which is typically called GP. And this outputs our H2. And then we go through our measurement device, and this is typically called GM. And then this will go back to the beginning of our system to output our error value. So to find the transfer function of this entire system, we need to have our H2 set point minus our measurement device times our H2. That'll give us our error. And then the entire thing is multiplied by our PID controller GC and our process GP. So this is all equal to our H2. So now we're just going to algebraically make this look a little nicer and get an actual equation for this. So we're going to have H2 is equal to our H2 set point times GC GP minus our H2 times our GM, GC, and GP. So now we can move our H2, GM, GC, GP to our other side to isolate our H2 variable. So we're going to have H2 plus H2, GM, GC, and GP is equal to our H2 set point times GC and GP. So now we can pull H2 out from this side, and we'll have H2 times 1 plus GM, GC, GP is equal to our right-hand side, H2 set point times GC times GP. So now we're going to divide this back over onto our right side, so we have our equation equal to our H2 variable. So H2 is equal to 1, or let's do it the other way, is equal to our H2 set point times GC, GP, divided by 1 plus GM, GC, GP. Okay, so based off of what we just did in the last part, now we are going to derive the transfer functions for the numerator and denominator of the forward and backward direction. So we're going to start out by looking at our numerator and denominator of our forward direction, which these are the values for that we found from CoLab. So we're going to start by looking at that. So if we have our numerator in our forward direction, that's going to be equal to 0.05 s squared plus 0.5 s plus 0.05, and then our denominator in the forward direction is going to be equal to s cubed plus s squared plus 0.25 s plus 0. So now thinking about what we just did in the last part, where we had our equation of 1 plus our GP times our GM in our denominator, we are going to start, we had 1 plus GC times GP times GM in our denominator. So we're going to start out by looking at that. So we're going to have 1 plus our GC times our GP is just the numerator and denominator of our forward direction. So we're going to have our num F over our denom F. And then we need to multiply it by our GC. So our GC is our transfer function in the backwards direction. So we're going to call that our numerator numerator b over our denominator b. And then on top we had our GC and our GP, so we're just gonna, on top, we're just gonna have our num f divided by our denom f. So now we can create a common denominator for the denominator of our equation. So we're gonna keep our num f over our denom f on top. And then to create a common denominator, we need to multiply by our denominator. So it's going to be our denom f times our denom b plus our num f times our num b. And this is all going to be divided by denom f times our denom b. So now we can multiply our numerator and our denominator just by multiplying by the reciprocal of our denominator. So we're going to have our num f over our denom f times the reciprocal of our denominator. So we're going to have our denom f times our denom b. And then it's going to be divided by the numerator, so our denom f times our denom b. Let me fix my spelling here. Okay, there we go. So we're going to have our denom f times our denom b plus our num f times our num b. So now we can see that our denom f on both sides will cancel. So we are going to end up having our numerator as our num f times our denom b over our denom f times denom b plus num f times num b. Okay, so now we can find the entire transfer function for our entire feedback loop. So we're going to define our transfer function for our feedback loop. And this is going to be in regards to our transfer function in the forward direction and our transfer function in the backward direction. So first we need to initialize our values for our numerator in the forward direction and our denominator in the forward direction. And these are going to be equal to TF2 poly of our transfer function in the forward direction. So we're just changing these into polynomials so it's a little easier to multiply them. But now we're going to do the same thing for our numerator in the backwards direction and our denominator in the backwards direction. So it's going to be TF2 poly of our transfer function in the backwards direction. So now we can return the equation that we just found on our whiteboard. So we are going to return poly to TF because we want these back into a transfer function. And we can do our numerator f times our denominator b. And then we need to have our denominator f times our denominator b plus our numerator f times our numerator b. So now we can try this out. So we are going to do TF feedback, and for our transfer function going in the forward direction, we are just going to use the transfer function that we found earlier. And then for our transfer function in the backward direction, So our transfer function in the backward direction, the only thing that is describing is our GM value. And we know that our GM value is just our measurement device. And earlier in this problem, we just assigned that a value of 1. So we are just going to create a transfer function of a 1 in the numerator and a 1 in the denominator. So now we can see that the transfer function for our entire process is, in the numerator, it's going to be 0.05s squared plus 0.5s plus 0.05, and then in the denominator we will have 1s cubed plus 1.05s squared plus 0.75s and then plus 0.05. Thanks for watching.